Hey guys, so today we will be building an artificial neural network, also known as a deep learning model for classifying various species of snakes. The idea is that we will show it an image of a snake and it will tell us the species of that snake. I'm building this for the HackerEarth Deeplearning challenge named Snakes in the Hood. As you can see from the problem statement here, we are required to build a sophisticated model that can classify the breed of the snake from its image. If we head over to the problem statement, we can see the details of the dataset that they have provided. We have a training and a testing dataset. Our task is to classify the snake breeds in the testing dataset and save them in a CSV file. This file will be uploaded here, and based on the number of correct classifications, your score will be determined. Then we also have a file named train.csv. This file basically tells us that in the train folder, a file called X is an image of a snake whose breed is named Y. And then at last we have the test.csv. This is kind of like your question paper. Given the image in the test folder, use your model and name the breed of the snake. So training a model occurs on our train dataset. Now the way I like to do things is I keep my training and validation dataset in separate folders. A validation data is the one whose answers the model tries to guess in each iteration. Then it fails because it's kind of dumb at that point and it checks the correct answers. This way the model knows where it went wrong and it corrects its mistakes, much like real life. To separate the training data from testing data, I started writing a Python script. The aim was that this script would copy 10% images of each snake breed class and paste it in the folder named validation data. The code for this script, much like everything else, will be available in the description below. Now the script worked perfectly fine, just the way it was supposed to, and it moved 10% data from each label class into a new directory. Now that I have my dataset set up, we can finally do some serious business. This brings me to step number 1, data preprocessing. I started by loading the train.csv into a pandas data frame. Here I found another challenge. You see, the names of the images in this file did not contain a .jpg extension, or any extension as a matter of fact, and without that Python will not be able to find its path in our file system. To solve this, I wrote a simple function which appends .jpg string at the end of the input argument. Then I applied this function to the image ID column in our data frame. I did the same with the validation.csv, and there you go, problem solved. Let's set some global variables for image dimension and batch size, and then we'll get down right to data augmentation. Data augmentation is something that can provide you an edge over the others. When new data is created based on the modifications of existing data, we call it data augmentation. I'll explain this in more details, but observe how I'm specifying rotation range, brightness, width shift to something called an image data generator. We will try to understand this in more depth. Let's take an example image of a bird here. Now, I can perform several different operations on this one picture alone. I can shift the image horizontally or vertically by different degrees of variance, or I can simply apply some random rotations on it. Each of these augmented images, they're like treated as a separate image file by your model. Say the test image was taken in a different lighting condition than your training data, your model would work just fine as it already has seen those kind of images. I found an excellent article written by this guy named Jason Brownie. He has given image examples as well as the code snippets on working with this image data gen API, and I, as a matter of fact, always find myself going back to this page. So I pass different attributes to image data generators such as rotation range, zooming and brightness, horizontal flips, and I use it to create what is known as a training batch. Now batches, as the name suggests, are like the group of data passed one after another through the model. We create training, validation as well as testing batches separately because they have different roles. Let's take a small look at our data now. You can see that this snake, although it doesn't look like one, the same image looks different due to the operations that we applied earlier. So with this done, let's move on to step number 2, building the model. We have about 5,000 images and we need to do classification of 35 different species. Let's do the maths. For over 5,000 images of 35 different classes, each class would have roughly 140 images. Well, that's not a lot of data. Even these 140 images will be divided into actual training and validation data. To make things worse, I realized that almost completely different looking snakes could belong to the same class. Look at these images, they belong to the same species and they look completely different in color and shape, I guess. That explains why the leaderboard had such a low score of around 40 to 50, I think. I realized that there was no point in developing a neural network from scratch. You see, the problem was A, we had very less and noisy data, and B, we had very large number of classes to identify. So to overcome this issue, we'll use a special technique called transfer learning. Now transfer learning is actually quite simple. I mean, I could show you some diagrams like this one or this one, but I think they are a bit confusing. Let's say that a really smart guy decides to build a super sophisticated deep learning model that has been trained over tons of data. It can make classifications of hundreds, maybe thousands of classes. Well, how about we use this model instead of creating everything from scratch? Our machine learning library Keras provides us with pre-built models. These have been trained over millions of parameters and are fine-tuned to achieve maximum accuracy. Like, look at this one here. It has an accuracy of 92% and has over 25 million trainable parameters. Let's pick the model named VGG16. Before training, I gotta make sure that it is compatible with my own dataset and classes. I use the TensorFlow Sequential Model API and simply add all the layers from VGG16 to that API. Now notice how I leave out the last layer. Well, that's because the last layer is the one responsible for setting number of outputs or classes. Next, what I'll do is I'll iterate through the layers of our model and set trainable equals to false. As the name suggests, this will hinder the layer untrainable, meaning it will not adjust weights during training. The reason being that we do not have crazy computational power for training all 25 million parameters. Also, these layers are well adjusted to classify 1,000 classes, so we'll take advantage of that fact and simply add some additional layers at the end of the model and train those instead. This way, the layers at the end will be the ones giving us final output. Now generally, I use the Adam optimizer and set learning rate equal to 1eneg5. Then I pass the batches of training and validation data that I created earlier in our model.fit and set the number of epochs to 30. Now, I'm ready to train my first model, but I gotta make sure that this model is saved once the training is done. I came back after a few hours when the model was done training, and well, as you can see, we get an accuracy of 28% and a validation loss of 2.65. But you don't have to be a machine learning specialist to know that this is a pretty terrible score. I mean, this wouldn't be a competition if it were that easy. This brings me to step number 3, testing and fine-tuning. You see, we will be making a lot of modifications to our existing model and try other models as well. But first, we gotta see how this one performs in the actual contest so that we can understand what we are looking at. Now, I set up some basic boilerplate functions which will process our testing data and make it ready for prediction through our model. This function picks up images from test folder according to the sequence given in the test.csv file. It does some resizing to the images, converts it to an array of numbers and returns a list of all the test images. At last, we use the model.predict function to make predictions on these images through our trained model. I save and write the results of the prediction in a CSV file according to the required result format and head over to the contest website to pass judgment. The judgment will be on the basis of how many images I predicted right, and I should say that my initial score wasn't very great. But that's okay, we have a long way to go. The first thing I tried was increase the number of parameters in the layers I added at the end, and I observed my score go up by nearly 2%. So my initial VGG16 model gave a score of 13.20. Once I tuned the parameters to be 512, it gave me a score of 15.86. But this wasn't good enough. So I did what every machine learning specialist does: extensive research. I needed to train more layers and I needed tons of fine tuning. But my computer isn't strong enough and it was taking 4 hours each time I'm training the model. I found a very effective technique. What I did was I set up a high learning rate for training the model initially, then I saved that model. After when the training was complete, I loaded the same model set a lower learning rate, and trained again. This boosted my score to another 3%. I tried many other techniques, but it was the best score I could get out of a VGG16. So I moved to the ResNet 34 models and I switched my library to Fast.ai. This was because I had heard a lot of great things about this library and always wanted to try it. I opened up the Fast.ai documentation and found out that it was a very high-level wrapper around PyTorch. It supported all the major operations required for building a strong and powerful machine learning model, and it provided image data bunch API, which is quite similar to image data generator in TensorFlow for processing the data. So I set up the environment and started coding. I followed the same 3 steps that I mentioned earlier. I preprocessed the data with image data bunch API, used something called a CNN learner for utilizing ResNet 34 model. I trained the model for same 10 epochs and observed quite a difference in my accuracy. My hope was to cross the score of 20%. I passed the testing dataset to this model, submitted the results, and I was shocked to see the results. I went up straight to 34%. I hadn't even applied data augmentation yet. I went straight to the documentation and found out that there's this method called getTransforms where you can specify image operations and pass it to the image data bunch. I also applied a very unique method of fine-tuning that I found online during my extensive research. Fast.ai provides this really cool method called LRFind, which gives you a graph specifying the relation between loss and learning rate during your training. Now the trick is to specify a learning rate where the slope is most downwards in this graph. There's a very detailed explanation in a repository by this GitHub user called Heromis, which explains the technique very well. After training my model once, I unfreezed the whole thing, which meant that each layer is now trainable. I highly recommend checking out this link for detailed explanation on fine-tuning a ResNet 34. I was pretty happy with the training results, so I passed the test set for classification and made another submission. I got 39.63, which was pretty great if you ask me. My rank was in top 16, but there were still 30 days left and I was sure it would drop to around top 50 by then. I tried many different techniques to increase my score, but this was still the best I could do. I was pretty satisfied by then and decided to end it there. So guys, by now it should be pretty clear that by no means am I a machine learning expert. I just know a thing or two. The whole point of the video was to tell you that if I can do it, literally anyone can. I would love to hear your feedbacks and suggestions. If there's anyone who attained a score higher than me, I would love to hear how you did it in the comment section below. Thank you very much for watching and goodbye.